Welcome into the Tech Ed Podcast. I am your host, Matt Kirkner, another wonderful guest for you this week. As you know, here on the Tech Ed Podcast, we are all about automation. We are all about robotics. We're all about innovation and working and talking with educators, industrial employers, leaders in technology that are doing really, really amazing things. This week is absolutely no exception. I am joined by the managing director of robotics of the Robotics Institute at the University of Michigan, and his name is Damen Provost. He is an amazing person. We're going to have an amazing discussion. Damen, welcome to the Tech Ed Podcast.
It's great to be here. Thanks for having me.
Welcome to the Tech Ed Podcast, where we visit with leaders who are shaping, innovating, and disrupting technical education. People who are not afraid to think differently, not afraid to try something new, all with the goal of securing the American dream for the next generation of STEM and workforce talent. So getting to know you, one of the things that's been most interesting is just looking at your background and looking at all the amazing things that you've done. It's really unique. It's really impressive. You spent time in the U.S. Air Force. Thank you, by the way, for your service to our country. You spent time with NASA. You have experience in early stage autonomous vehicles and so much more. How does someone rise to the position of managing director of the University of Michigan Robotics Institute?
Well, I think there's a lot of luck that goes into it. First of all, my background, I like to say my first autonomous vehicle went 21,000 miles an hour and weighed 11,000 pounds. I got to work with X-37 back when it was still a NASA project and I was in the Air Force, and they were doing drop testing out at Edwards Air Force Base out in California. And, I thought this was such a cool kind of creation, something that you could launch on the top of one of these rockets, fly around in orbit for some amount of time, and then they hit a button and then it magically comes and lands on the ground with, no human in the loop there. And, I was kind of hooked on that from, autonomous vehicles and what robotics could do in space from then on. I went more into kind of the larger communication satellite space with industry. And then I came out to University of Michigan about 10 years ago, worked on a constellation of small microwave size satellites called Cygnus. We launched those in 2016. And kind of around that time, as we're getting ready to launch, I was figuring out what to do with my next chapter. The autonomous vehicle scene in Michigan is pretty busy back then. I think a lot of companies like Ford and Toyota were really getting into the area. So I kind of started dabbling in there as a research engineer with one of our big labs. And it got me hooked. And so I went kind of full robotics back in 2017. And for the last 5 years, that's kind of all I've been doing.
And we're really looking forward to getting into that role as a managing director, the things that you're doing, the things that your institute is doing. As I've gotten to know you, Damen, and as we've talked a little bit about technology, you regularly use a word that I hadn't necessarily heard too often before, and that word is roboticist. And you use this term throughout your programs. What, for our audience, is a roboticist?
So I like to start out, it's kind of the idea of what is a robot? And you ask 10 people and you probably get 11 different answers. We kind of start out with the idea of embodied intelligence. We break up our grad program and kind of the foundations for robotics into these three kind of pillars. So sensing, reasoning, and acting. Sensing is the idea of that something can go out there, perceive the world around it, dealing with computer vision, LiDARs, radars, cameras. The reasoning, the planning, that AI machine learning, figuring out what you're going to do once you kind of assessed your scene and how you're going to do it. And then the acting is going out and doing it. So the kinetics, the dynamics. So that's kind of like what we think of as a robot. And so like a roboticist is someone that kind of is an expert in one or two. And sometimes, in these rare cases, maybe three of these areas, but they at least understand how they all interact together. So they can go out and they can work on algorithms, they can work on the software, they can work on the hardware. And so that's when we think of what a roboticist is, there's really a lot of different definitions, because you could be really strong in programming or really strong in building. And, we look at you and say, yeah, you're one of us, you're a roboticist. And that's I think the key is kind of the passion for working with these embodied intelligence, smart machines.
And it's interesting as you use those terms, sensing, reasoning, and acting. And we talk about that in the field of robotics. It's really what we as human beings do as well, right? I mean, we go through life, we're sensing our environment. We're taking whatever we're seeing, feeling, hearing, tasting, and using our ability to reason, and then acting on the basis of that. And so as we kind of look at, what some have called the singularity as the future unfolds itself, and as we look at robots and autonomous vehicles and really anything using artificial intelligence, becoming and thinking more and more like people. We're really on the verge of some really interesting innovation. And then we combine that with an entire career or an entire job. So for our audience members who may be students, maybe young people considering the future, a roboticist would be an individual that specializes in one or more of those areas in terms of robotics, sensing, reasoning, and acting. Some amazing careers that are available to roboticists, and you're no stranger to them. You work all around a number of people that have that title. You mentioned, as we talked a little while ago, about your background, Damon, and you talked about your relationship earlier with Ford. You continue to have a really good relationship with Ford, in which 100 roboticists are performing work and research in your facility. So tell us about that. Do your students get to interact with these Ford roboticists, and how does that interaction benefit those that are working in your program?
That's really cool. So we just moved into this brand new building. It's about 140,000 square feet, 4-story building, and it's the Ford Motor Company Robotics Building. I think the interesting thing is that, those 4 stories, kind of the University of Michigan, this is right on our academic campus, right in the heart of the College of Engineering. And so that top floor, we have those Ford roboticists up there. They have a high bay garage down on the first floor too, with some of their cars as well. Michigan and Ford, we've had a relationship going back 100 years. And I think for robotics, that industry component is super important. There's all these kind of cutting edge problems that industry deal with on a day-to-day basis. You think of academic research, we're more on that 5 to 8 to 10 year horizon, looking out into the future there. So when you can partner with folks that are working with these really like cutting edge problems like Ford or Toyota, we have lots of great partnerships with Northrop Grumman, the aerospace companies out there, figuring out, what are the problems of today? How can we shape our research going forward? And then also, from a job perspective, right? Our students are coming through, they're getting this education, but, their eyes on the prize. They want to see, what am I going to do in the next, 3, 5, 10, 50 years of my career? Are there the avenues? So having Ford is great. And we've done some interesting things from basic research. They sponsor some of our student teams that go out and do these competitions that we can talk about a little bit. And we've brought them in to actually teach some classes too as well. So it's been a really nice partnership, even though we've only been like cohabitating in the space for just a little bit over a year now.
What an amazing opportunity for your students to interact directly with these folks that are already working in industry. I really like the fact that you began that answer with the importance of these industrial relationships and really of doing applied research and doing research that is going to benefit industry, that's going to have applications as we continue to innovate in the world of industry. And in as much as the Tech Ed podcast is all about what's going on both in education and in industry, you've really struck both of those chords really, really well. So impressive things going on at your institute, Damen Provost. I want to talk now about the University of Michigan Board of Regents, and they recently approved the creation of a new Department of Robotics. This is really unique for our listeners that may not be aware of this. It's the first of its kind, believe it or not, by a top 10 engineering school. So in as much as robotics and automation is so very important, and it's really permeating so many aspects of engineering programs, so many aspects of higher education. This is the first time that a university has created a department specifically dedicated to robotics, especially as it relates to top 10 engineering schools. Can you share a little bit about this initiative and what you think makes it unique?
Robotics has been happening at Michigan for decades, but it's kind of been in the silos of mechanical engineering or computer science, aerospace. We have a naval architecture department. So there's been all these roboticists that have been, in the infrastructure here. But it was really in 2012 when we kind of had this critical mass of folks that said, I like robotics, you like robotics, she likes robotics, let's start doing robotics together. So we launched an institute with a grad program. We said, hey, let's build this, this new robotics building. And that's just been building up over the last 7-8 years. So our grad program now is about 230 grad students and master's and PhD students. We're the number 2 ranked grad program in the country. And we said, we've been looking at what we've been able to do with that. And we said, we think there's a lot of demand from an undergraduate perspective. At our university and most universities, if you want to have an undergraduate degree, define the discipline, which we've been trying to do, and you need to have a department so you can have the right faculty and resources and researchers come in here. So that was a kind of a momentous thing for us. We spent a lot of time planning that. And I think what makes us a little bit different, we haven't come from a computer science department. We haven't been an offshoot of mechatronics and mechanical engineering. We have researchers, we have have about 30 faculty in 12 different departments. And so it's mostly engineering, but we also have folks from the School of Information and kinesiology. And we've really looked at robotics from a diversity, equity, inclusion standpoint too. So that's something that we've looked at both from the people that are making up the Robotics Institute, but then also the ideas. The diversity of ideas, I think, is really important to solving these really hard problems. And when you look at the makeup of it, we have people from a controls background, we have people that come from the AI lab and computer science, and they're all able to come together in this one spot here, and their students are able to interact as well. So, you have this really cool menagerie of all these groups coming together and making something that's very unique, I think, not only for Michigan, but for the broader robotics community. We've seen other schools that have done similar things. Worcester Polytech has a great program in robotics there. Carnegie Mellon, you've been able to get a dual major in robotics for a while. But I think kind of trying to set the tone of going off and establishing a real department of robotics is going to lead to new opportunities for faculty, students, and I think the robotics field as a whole.
I think you hit on some really interesting points there, Damon. The first thing is the whole idea of I like robotics, you like robotics, she likes robotics. Let's do robotics together. I love that. I love the idea of bringing different viewpoints in different backgrounds together in terms of innovating, in terms of learning. And obviously, that's a key tenet of the work that you're doing at the Robotics Institute at the University of Michigan. I think you're exactly right. I think that any business, any educational institution is better when we have as many different backgrounds and points of view represented. And it's great in terms of innovation. It's great in terms of ideation. And I think it's also great in terms of making sure that whatever it is that we're innovating applies to a wide variety of individuals. So some great things going on in that regard. And we look forward to watching what happens as, again, this first top 10 engineering school robotics program continues to flourish and continues to grow. When people think of robots, and I'll be honest, even myself sometimes, Damon, I think of a 6-axis industrial robot. I spent my 20-some years in industry. I certainly saw plenty of assembly robots and sorting robots. We saw paint robots. And I think for most people, when they think of robots, that's what they think of. In fact, we had Mike Chico, who's a great friend of ours, president and CEO of Fanuc America, on the largest industrial robotics company in the world. He joined us last year, talked all about the world of industrial robotics, but really industrial robotics, as important as it is just one aspect and one discipline within robotics. Your research and your education programs include things like drones and AI, autonomous vehicles, bipeds, and all kinds of different aspects of robotics. So what various technologies and disciplines are encompassed by the University of Michigan Robotics Institute? And can you contrast the preparation of your students for these myriad technologies with the idea of what you call the full stack roboticist?
That's a great question. So, I talked about the sensing, reasoning, and acting. That's kind of one axis. We also think of kind of the environments. So at Michigan, we have robots in space, we have robots in the air, robots on the ground, robots underwater. We're kind of one of these big spaces that can support all this research. So I think right now Michigan has something like a dozen satellites on orbit. We have 2 ground control stations. We have a Mars rover yard kind of modeled after JPL's big Mars yard out in Pasadena, right next to our building here. So we have a lot of interest out in there. From drones, we have M-Air, which is our large netted drone test facility. It's about 500,000 cubic feet. It's a really big net space for flying these drones. Inside our building, we also have a drone space. So we're up here in Michigan winter. We do like to think of Michigan winter as a feature, not a bug, when it comes to robotics and testing robots. No offense to the folks in Palo Alto or Chandler, Arizona, but if you're just driving, your autonomous vehicles around there, you're not getting the snow, you're not getting the potholes that we have to offer here. And we do like to bring our robots out into the real world here. I think from our standpoint, we want our students to get their hands on hardware. We want them to be able to build in the shop. The new building has a large maker space here as well. You mentioned the full stack roboticist. Yeah, we kind of co-opted that term from programming, the full stack programmer, but understanding the idea that how the algorithms work, you're able to understand the software and you're able to build the hardware too. And maybe you're not an expert in all 3 of those, but you can understand how they interplay together to make one of these really complicated machines work together.
Just thinking about all the different aspects of robotics. And again, as we think about industrial robots, maybe folks think about things like programming a robot, understanding macros, understanding dual check safety, understanding how to jog a robot, applications for end of arm tools, and so on. These are all really, really important applications, but you're going even deeper than that and much deeper than that, into the sensing, into the reasoning, into the acting, talking about the algorithms that sit behind this technology. I'm working on a project in the state of Wisconsin right now as we're looking at how do we educate industrial employers around artificial intelligence. And one of the things that we talk about there is you really have to understand this whole world of algorithms. You don't have to be an expert on it, but you certainly need to understand what an algorithm is and what's going on in the background, whether it's a robot or any other application for artificial intelligence in the world of industry. And you're touching on all of those things and kind of coming back now to this idea of embodied intelligence. And you mentioned that earlier in our discussion today. We talked about sensing, we talked about reasoning, we talked about acting being those three disciplines. Can you go a little bit deeper on each of those and tell our audience, when you talk about sensing, reasoning, and acting, what are we actually teaching and learning?
For sure. So one of the things we tried to do with robotics was not recreate the wheel. There's a lot of these really great classes that have sprung up through computer science and electrical engineering. And so we've kind of tried to take the best of all these worlds. And so from a sensing perspective, perception, ideas of looking at remote sensing, figuring out how these sensors work in different environments as well. And it's interesting when you start talking with folks that have been doing this. So, computer vision is big in electrical engineering, but also naval architecture. Right. So, we think about one of these underwater robots, you're going through different layers, different salinities, different temperatures. And as you start going down, the light starts disappearing. So being able to have that kind of ability to make sense of what you're seeing when you go underwater, and then you get down to the bottom and your propellers hit a gunk and everything goes dark there as well. So taking kind of those specific domain areas as well for the sensing and figuring out kind of what you're seeing out there, that reasoning, the simultaneous localization and mapping here, the SLAM algorithms that you always hear people talk about. So when you put a robot into a maze, we have these LiDARs that come on for all of our first year students, whether it's at the grad level or the undergrad level. We give them these little M bots. It's got a little 2D LiDAR, a little perception camera system, and then they have to go and build a map of what's around them. So, understanding kind of how that all interplays together. And then it's like, okay, you've built this map, you're in this maze. Now we have an objective. We want you to get from point A to point B, figuring out how to get to that objective and then moving it. So, whether it's a leg stepping, whether it's a propeller spinning, whether it's a biped running, all those kind of controls and motion planning that have to turn into actually something that moves here. And there's going to be consequences. So, each one of these things, you're going to have new information every time you change wherever you are. So you're going to have to rebuild that map, re-look around, see how your change has changed your current state and how that's going to affect your ability to get to whatever objective you had at the beginning. And sometimes you might find out that, your objective has changed. And so being able to replan that on the fly is important too.
One of the things I noticed about you, Damon, right off the bat is you have and I mean this genuinely, you have a gift for taking really, really complex ideas and concepts and boiling them down to simple terms and simple explanations that maybe the non-technical folks can understand. I have to tell you the highlight of that in your last answer was when you used the example of the propellers hitting the gunk underwater. I think that's something that every one of us can relate to. So just awesome chatting with you about this, because you do have such an ability to bring it down to earth and help those that maybe aren't as familiar with all this really high-tech terminology, understand what it is that you're doing at the University of Michigan Robotics Institute. I want to talk now a little bit more on the whole topic of higher education. Regular listeners to our podcast know that I had my share of frustrations as I was going through the traditional education pathway. I always had a hard time, sitting in a classroom for hours on end and listening to a lecture, trying to stay glued to a textbook for more than about 5 minutes at a time. There are people who can do that. I just wasn't one of them. And I was always the person that wanted to get my hands on things, that wanted to understand it, wanted to understand applications, show me what this means in the real world. And now I can grasp it. And now I can build on that learning. Not everybody's like that, but I'm certainly like that. And I think a lot of folks that find their way into STEM careers and find their way into STEM education are like that, right? I mean, you don't study engineering just because you love calculus, right? You want to see how this stuff manifests itself out in the real world. And I'm a believer, and I think you are too, that higher education in so many ways is going to be disrupted within the coming decade. So let's talk a little bit about how that's going to happen. You have some really interesting ways of teaching math. We talked about utilizing linear algebra in an applications-based sense and format. So let's explore that for a bit here. Let's talk about the different ways that you see teaching math, teaching linear algebra.
So I'm a project manager, system engineer, kind of has been really what I've been doing a lot of my career. And, I like to figure out, what are the requirements? What's the problem? And then let's start backing up and figuring out what are the impediments here. So that's how we kind of started our grad program. We want people to build awesome robots. How do we get there? And then as we have this grad program, we're looking at the undergrads that are coming in. We're like, well, how could we build even stronger grad program if we had stronger undergrads? So we've started really from their first year, and we've been re-looking at how we're teaching them when they come in here. And I think we're thinking about it with that same diversity, equity, inclusion lens here as well. Our fundamental belief is that we have this kind of equal distribution of talent around, but there's an unequal distribution of opportunity. So whether you have students that go to maybe the best private school in Manhattan, or maybe you have schools that go to an underfunded urban school in Detroit, or some rural areas that don't have access to, all those calculus AP credits or programming. We want to say, when you come in here, we're going to give you some skills, and we're going to allow you to succeed and build on those skills and keep succeeding as you're going through the program. So when we started off robotics and AI and data science, really, so it's not just kind of a robotics bent, but linear algebra and programming are two real key areas for getting these students up to speed. The beauty is that every high schooler that's coming in has taken some sort of algebra. So, linear algebra is kind of a natural progression for what they're doing here. And we start with, just very kind of accountant level matrix vectors and matrix multiplication. And when they come in, they do it by hand. And then we say, all right, well, you can keep doing it by hand. You can multiply a 20 by 20 matrix, or you can learn about programming and make your life a lot easier. So we've introduced Julia, which is like a fully object-oriented programming language, but it's close enough. You can run it in the cloud here. So whether you have a $200 Chromebook or a $5,000 Apple book, it doesn't really matter, because you can kind of do all your compiling and running in the cloud here as well. So again, that it kind of takes that resource edge off for the students that are coming in. And when we're teaching it, we try to think of math as you would learn it like you would to use something in the shop, right? So you go to use a drill press in the shop. Now, if you learn that and say, okay, well, come back in 4 years and maybe you'll be able to use it for something interesting, no one's going to really find that interesting. And no one's really going to want to do that. But if with our linear algebra course, we give them projects, so they're able to learn the math and then actually demonstrate it in a real world problem set and go out and say, yeah, this makes sense. This is a useful thing for me to learn. And then that kind of feeds the fire where they want to learn more and more as they're going forward with this. So with our first course that we did, that Rob 101, the computational linear algebra, we would give the students a data set, a LiDAR point cloud from Cassie, which is one of our bipedal walking robots, and say, okay, go build a map with all this point cloud data. And so, you're thinking about what this looks like in Cassie, one of these biped robots, they have this really kind of pronounced side to side motion as they're walking. So, you have to figure out the coordinate frames, put everything, moving this data around. And again, whether you're a roboticist, whether you're data science, whether you're just going into, some other related field, having those kind of skills is kind of critical to developing the workforce for the future.
I barely passed my high school algebra class. If I had been able to learn algebra in the way that you just explained it, let's understand some formulas, let's understand a little bit of theory, and then let's go do it. This whole idea, so much about math I learned actually working on manufacturing floors and having to solve puzzles, having to solve problems. And you're out there doing complex calculus in your head trying to solve a problem, not even realizing you're doing it. What a great way to inspire young people of all ages, to show the aspects of applied math. So great work there. I also want to explore this idea of open source curriculum, because a lot of what you're doing there, you're not just limiting to your students. You're saying, look, let's make this available to anybody who wants to learn. Explore that a bit for us.
Yeah, so actually, when we created this class, we did it in partnership with a faculty member down in Morehouse, down in Atlanta. So Dr. Joseph, it was this idea that, hey, we have a certain student that comes here, but again, going back to that DE&I, our expectations may not align with kind of the broader expectations of students and what skills they have as they're coming through here. So we wanted to develop this in an open way and then kind of share it as well. So what we've started doing is posting all of our classes, all of our lecture notes, all the software and programs on GitHub and on YouTube. So people can go out there and they can kind of download the whole course. Even the textbook has been open source here as well, because, frankly, there's a lot of catching up that we need to do as a country. And so having kind of these resources out here that people can take and start implementing. I mean, one, it's for us, we want to have better roboticists and better people coming into our pool as well. So whether it's happening at Michigan or whether it's happening at Brea, which is another university we've been partnering with down in Kentucky, we're really looking to expand the footprint of robotics. And there's huge demand, right? I mean, what we've seen out there with FIRST Robotics and VEX Robotics from a high school level, I mean, they're these students, these hungry, ambitious students that are going through these middle school, high school programs and these big competitions. And when they come to college, they want to keep doing that. They want to keep building. They want to keep creating. And so, we want to make sure that you're not limited to, one of these top universities. This is a curriculum that we think that we could share quickly across a broad spectrum of folks here. And so we've done it with 101. I think we have 5 different classes, starting from freshman year classes all the way up through our graduate classes now. So we're doing mobile robots is a class that's being taught right now, which is a graduate level class for mobile robotics. We're doing the same thing where, again, you can get all the lectures, you can get all the videos, you can get the homework assignments, all on GitHub right now, which has been a wonderful asset.
That's such a refreshing way to look at higher education. I was having a conversation not too long ago with the dean of it's an engineering school that everybody in our audience would recognize, a very well respected engineering school. And one of the things that he said to me was, he said, in many ways, our engineering curriculum hasn't changed in 30 years. He said a lot of what we're teaching now is what we were teaching 30 years ago. And you think about, certainly the principles don't change, the principles of physics. These things are what they are, but their applications are so different. And to think about a faculty member that is still teaching math, still teaching calculus, still teaching any aspect of engineering, the way that they were teaching it in the year 1992, I mean, that's a little bit scary. And really, higher ed, we talk about disruption, and we have a lot of listeners that are busy in higher education. We have to start innovating, and we have to start thinking about things in new ways. And we can't just think about this as, I have tenure. I don't need to think any differently about my curriculum or the way that I'm delivering learning. A lot of folks don't like hearing that, but I'm a really, really strong believer in that. And just to listen to you talk, Damen, about how you're innovating curriculum and then taking it and saying, as a faculty member or as a leader in higher education, I may own that curriculum, but that doesn't mean that I can't share it with the masses. And to the extent that you can, and you can inspire people around what you're doing, that's just going to come back and benefit you. And I think that is really the theme of higher education as we move forward. So that's just a really fascinating way of looking at this.
We have a culture of open sourcing a lot of our research as well. So one of our researchers, Elliot Rouse, he's a researcher in prosthetics. And, one of the issues, again, too, where you're trying to compare results with a robot and trying to, repeatability is a big issue. When you're talking about a prosthetic leg, you have both robotic part there, you have the algorithms, you have the hardware, the software, then you have a person that's in the loop too. So repeating results across platforms could be really, really tricky. So National Science Foundation, they actually funded him to develop an open source leg. So you can go to opensourceleg.com right now and get all the CAD for this leg. You can go to GitHub, download all the software, and he has videos to show you how to put it all together. And so for, again, about the price, I think it's about $30,000, which for a research lab, that's, a manageable amount of money. You can go and get your own open source leg. And I think there's probably about a dozen universities using this as well. We're also developing an open source first responder bipedal robot here from Jesse Grizzle's lab. So in Manny Ghaffari. So it's one of these ideas where we have these great ideas from a research perspective. We think we have great ideas from kind of an educational perspective as well. And going out there and sharing this is really important for us. And I think the field as a whole.
We talk about algorithms. I will tell you right now, the Google algorithms are busy trying to figure out why so many people are looking at opensourceleg.com. Who knew that was even a thing? But a great example of how we can share, as you suggest, not just curriculum, not just applications for learning, but also applications for research and helping people build on other people's research. Why reinvent the wheel if somebody else has already come up with something? And credit to you and the University of Michigan for sharing that research and those results in such an open way. We've already touched on a little bit on VEX Robotics, on FIRST Robotics. My wife, Renee, and I are huge supporters certainly at First Robotics, and we support First Robotics teams, and a number of them in a number of different ways, not just financially, but also helping them with innovation, helping them with things like design for 3D printing and additive manufacturing as they're innovating. It's just amazing watching these young people participate in these competitions, all the creativity, all the problem solving, and not just on the engineering side, but on the marketing side, on the financial side, really learning how to run small businesses in many ways as they're going through these programs. So these students, they go through First Robotics programs. For our audience members who have seen a First Robotics competition, you know how inspiring this can be. And these students are just on fire with an interest in technology, with an interest in innovation, with an interest in engineering. And we inspire them toward education pathways in engineering, and they get to engineering school and they are so fired up to continue this learning. And we stick them in a classroom and we teach them calculus, or we teach them physics. And in a lot of ways, I think historically, those courses have been used maybe in some ways to weed out engineering students. And if anything, we have to find ways to inspire more engineering students. So I know you've experienced this, you've seen this. They run into this wall of calculus, all of this challenging math when they arrive at their undergraduate engineering programs. What are some ways that we can maintain the interest and the passion that these students have around technology as they're transferring from really cool applied learning while they're in high school into the university setting?
Yeah, for sure. I mean, I am pro calculus. I am pro physics. But I agree. You know, I think your point earlier was that we've been kind of doing it the same way for the last 30 years, and we need to be able to engage these students better. And so I think having real kind of design-based work, doing project-based learning, is key to I think unlocking this next generation of students here. So in addition to those math classes we talked about, we get them to build robots that first semester too. One of the things, unfortunately, we've seen from middle school, high school, that the shop has kind of gone away, right? And so that hands-on experience, the students are getting through First Robotics if they have the teams and if they're lucky enough, but lots of students don't have that. So we want to bring them in and get them familiar with the shops and being in there. And frankly, we talk about there's sometimes a bro culture in computer science, and unfortunately sometimes in robotics too. And so we want to bring everyone into that shop here from their first year. So there's no kind of fear or kind of tentativeness of being able to go in there. Understanding how the bandsaw works. We do a lot of additive manufacturing with 3D printing. We have laser cutters. We want students to be able to go in there and build these robots in a collaborative manner, feel welcome in this environment, and feel like they belong in this environment. And once they start doing that, then they start feeling like they belong in all these bigger challenges. We also, like to teach them that these simulations that they're doing are doomed to succeed, is a phrase we like to use. They're going to do it all in simulation, which is super important, but then they're going to go out into the real world, and we want to have that experience where they go out and their motor breaks, or there's more friction from the rug, or there's different friction from nice smooth floor, and understanding like how those change and how they need to go back and adjust their algorithms or tune their code up to deal with these kind of challenges.
Yeah, learning from problem solving is probably, at least for me, the best way of learning, right? Nothing ever works, certainly in the real world. As somebody that ran manufacturing operations and innovated in manufacturing for a couple of decades, nothing ever worked the first time. I mean, when I say ever, I can remember a single new production line implementation, a process change, a quality improvement, the result of a Kaizen event that ever worked the first time that we did it. And so learning by failing is actually a great way to learn. So many different ways for us to deliver learning and excite students as they enter their undergraduate engineering pathway. I didn't mean to insinuate, by the way, that you were not pro-calculus or pro-physics. Without question, that's the reality of the engineering world that we live in, but making sure that students are both inspired as they're learning and then understanding the applications of what they're learning, and maybe some of those more challenging classes and courses is really, really important. I want to coin a term for the purposes of our discussion. Let's call it the democratization of engineering pathways. You've mentioned a couple times, Damen, how important diversity, equity, and inclusion is in terms of your programs, how important it is to make these opportunities available to everybody, to students, regardless of their background, regardless of where they come from. I know in many ways you're using technology to do that. Tell us how technology is making careers in engineering more available to students from all backgrounds.
Well, I think, just what we're doing right now, we're here, we are on Zoom, and, having this conversation from thousands of miles apart. When we ran Rob 101 for the first time, we actually ran it remotely with Morehouse and Spelman, two HBCUs down in Atlanta. And actually the whole thing was planned pre-pandemic, right? So we were planning to have them remote join this class. And all of a sudden the pandemic happened. And when we had to go remote, then everyone was remote. So, it's like it really was able to kind of seamlessly go forward here and bring in all these people from these different areas to collaborate together. That's a big thing that we see from a technology standpoint too. Things have gotten just cheaper as we've gone forward here. So the ability to get your own robot. I mean, 10 years ago, this is, even the cheap ones are, thousands of dollars, tens of thousands of dollars. We've been able to develop a nice small learning package that's, again, open source for other people to get out there, our MBot. $200 for a pretty nice educational build your own kit here. Again, a robot that can run SLAM. So it's something that can do kind of everything an autonomous car could do, but you can't go 80 miles an hour. You can go maybe 1 mile an hour. But again, it's the same math that kind of goes into there, and being able to go online, download that, go to McMaster, add all the parts to your cart, send out for boards. It's getting really easy for people to be able to build these things, even if they don't have maybe a full maker space wherever they are. They can order this a lot online and have it shipped to where they are here. So there's a lot of cool things that have been happening in that technology space.
Common thread that runs through our discussions on the Tech Ed podcast is this whole idea of the exponential economy, products doubling in price performance every 12 to 18 months. I had a conversation with Dr. John Carrier from the Sloan School at MIT a year or two ago, and we talked about how smart technology is literally becoming more affordable by orders of magnitude. So that something that was $10,000 is now $1,000. Something that was $1,000 is now $100. And you're saying that the same thing is happening in the world of robotics, that, several years ago, a several $1,000 robot would have been absolutely out of reach of probably just about any student if they wanted to experiment at home. And unless they had an opportunity at their school where they had access to that kind of technology, those were the students that didn't have the opportunity to be inspired toward these types of careers and pathways in engineering and in STEM, and toward a career like being a roboticist. And now, as these applications and as these experiential learning opportunities become more and more affordable, in large part because of the exponential economy, we're now democratizing in some ways the opportunities for these students to learn more and more about technology, regardless of their background, regardless of their financial wherewithal. So what a great thing that's happening in STEM education. Another great thing that's happening in STEM is your partnership with Marygrove High School. It's in collaboration with your university's education department, by the way. So we love to see, so many times in higher education, you see different departments maybe with diverse and diverging interests and having a difficult time partnering. In this case, you're partnering with your university's Department of Education and inspiring young people from underserved communities toward opportunities in STEM. Tell us about the project with Marygrove High School.
Yeah, like you said, our School of Education and Demoji there, they've really been pushing this. Marygrove, it's now a public school in inner city Detroit. And it's kind of an extension of what we've been doing with robotics from the graduate level. We said, well, what works here? What can we share at the undergrad level? And then again, you start backing up. And it's like, all right, well, what do our high schoolers? Marygrove's looking at the whole P20, the whole life cycle of preschool from all the way through college and beyond, and how we educate these students here. And so, we've had just a small bit of what they're doing there to kind of help shape, their robotics curriculum. They have a maker space down there because, again, they're like, yeah, this is important. The students, they want to come in here, they want to build, they want to, develop these things. Michigan, but besides Marygrove, we have the Michigan Engineering Zone, which is in downtown Detroit. The MES is a hub for these FIRST robotics teams. Again, it's a makerspace shop where all these students can come together and build. And we just kind of think that this is, again, a model that we can develop here and then implement everywhere. And so I think having great partners like this, the city of Detroit is obviously an important part for Michigan. And I think working with them to really revitalize what's going on down there has been very exciting for our faculty and our students as well.
And it's been great to watch the renaissance, to use that term that's been used in other cases around the whole Detroit area, watching that area bounce back from really some incredibly challenging economic times as their economy and as their industry has changed. And so great to see you being a part of that. Great to see you inspiring those young people at Mary Grove High School around STEM, around technology, and around engineering. It's really, really important work. What a unique approach that you have to higher education, to research, to industrial partnerships, to partnerships with other institutions of higher education, your high schools, and so on. Just a great conversation we've had today with Damen Provost, the managing director of the University of Michigan Robotics Institute. We're going to close our time today, Damen, with asking you a question that we ask every single one of our guests here on the Tech Ed podcast. So you've done some amazing things, and kind of pulling from that background and dwelling on that for a moment. If you had one piece of advice from all that experience that you've had for a high school sophomore, what would that piece of advice be?
I think this would be the same advice I give for them or really anyone else is don't be afraid to fail. As roboticists, our robots fail all the time, right? I mean, we've caught in fire on the Discovery Channel. ESPN Game Day was here shooting their promos live for the Michigan-Wisconsin game. And they said, well, bring down a robot and we'll have some fun. And we brought down Cassie, our walking robot. Camera goes live, and like 2 seconds later, the robot falls over on live TV. And it's all part of the experience, right? I mean, it's learning, failing, learning from those failures, and failing in a different way. And then sometimes you're lucky you eventually succeed as well. I mean, I think that's the thing that I would tell anyone in high school is that don't be afraid to fail, because we all make mistakes and we all have failures. And I think the resilience that you can learn from those failures is something that's going to serve you well throughout the rest of your career.
Without question, the whole idea of not being afraid to fail, learning from your mistakes, your story there. I've never had a robot catch fire on the Discovery Channel, but I did have my largest customer in my plant one time visiting us, talking about some damage that was happening to their production parts as we were processing them. And as we're talking about it on the shop floor, one of our material movers comes around the corner with a fork truck full of parts, full of containers. And the containers, inertia and physics being what they are, continued in one direction while the fork truck continued in another. And the parts spilled all over the floor right in front of the customer. Probably the biggest, on-spot failure that I can remember. So never a robot catching fire, never failing an ESPN, but that happens to the best of us. And we learned from that, right? We learned from that experience in a lot of different ways, and it made us better. So nothing ever works right the first time. We continue to work at it. We continue to improve it. That's exactly what you're doing at the University of Michigan Robotics Institute. Damen Provost, its managing director, has been just a fascinating guest for us today on the Tech Ed podcast. Damen, thanks for spending some time.
Thanks so much. It was a good pleasure.
Thanks for joining us for this episode of the Tech Ed podcast. If you haven't already, subscribe, leave a review, and if you liked this episode, share it with a friend. New episodes launch every Tuesday, so listen in next week.